Okay, let's keep it on time. Before we introduce the speaker, I just want to say a few words. Today we are very pleased to welcome the leadership from Meviang. We are honored to have Dr. Tina Yu. She's the president and CEO from Meviang. She's not just any CEO, she has a PhD from Princeton in biophysics. She's leading the innovation in Meviang, really changed the landscape of proton therapy. And also we have Dr. Townsend, Zwart, right? He before he joined Meviang, he was working for Harvard, MIT for decades. Really, he's an architect, really driving the single cyclotron accelerator in Meviang, make it smaller, easier to access for proton therapy. And we have Leo, is a VP for sales, right? Thank you guys for visiting UCI. Also, we have our Greg Peterson, he's a CEO from Sandoz. Thank you guys for visiting UCI. Also, we have UCI faculties across the campus. We have our associate chair, vice chair for research. Is it the same or different? It's the same. Dr. Sabri Molloy, he's going to introduce the speaker later. And we have Dr. Charles Dimoni is the vice chair for research for radiation oncology. And we all know he's a pioneer in flash radiotherapy. Together with Peter Maxine, he's a vice chair for metaphysics. They work together for pushing the flash into clinical practice. And also we have Goodkin here. We have many other faculties here. And also we have, did I miss anyone? We will have people keep coming in, but you guys enjoying food where we have the lecture. We also have people from on Zoom from radiology. I see a couple of Eleanor is there, and also we have people from radiology. We have Dr. Sue there. We even have people from Oklahoma. So I have a long-term collaborator, Dr. Yung Chen, and his students is here. Srini, thank you all for coming to join the seminar. I think cancer treatment is very personal to me because I lost my mom when I was very young to cancer. And also I lost my older sister when she was at age of 42. So I really devoted myself into cancer research. Really, I would do everything to bring cancer care to like more precise, more accessible, and Maven is really just doing that. And they're the first company making a single room proton machine. They're the first company that can feed the proton machine into a traditional LINAC valve, which I believe is huge. And I believe eventually it's going to be widely adopted in clinical practice. And it's amazing. So also, my lab has been working with them in the past several years. We have been always working with the Meviang machine in Oklahoma. We did everything all the way to patient study now. We have IRB protocol in Oklahoma. And now we have a startup, it's called Sandoz, and Greg and I are trying to integrate some of our technology to Meviang machine. Hopefully we can really start the journey and treat the patient more precisely and has more access to the proton machine for all the cancer patients. So with that, I would like to have our Vice Chair for Research, Dr. Sabri Molloy, to introduce the speaker. Here? You can use the microphone.
Okay, welcome everybody to this month's research seminar titled Proton Therapy: Rising Quality, Compactness, Accessibility. Our speaker, Dr. Townsend Zwart, he's an accelerator physicist. Has his AB in physics from Dartmouth College and Ph.D. in applied physics from Boston University. He He's a principal architect of the Mivion S250 series proton accelerators and has been pivotal in Mivion's innovation since 2005. He played a key role in designing the world's first compact 250 MeV superconducting synchrocyclotron, earning multiple patents for his work in accelerator technology and pencil beam scanning. His groundbreaking contributions have advanced proton therapy, making treatment more precise and accessible. Prior to Mivion, Dr. Zwart contributed to proton therapy advancement at the Harvard Cyclotron Laboratory and has spent over a decade at MIT as a research scientist, developing cutting-edge accelerator systems. Looking forward to your talk.
Thank you very much. Can you hear me? Yeah. And thank you, Sean, for the invitation. It's really, it's wonderful to be out here in Southern California. We have 5 inches of snow back in New England and school is closed down. So here we go. And Dr. Chen, it's nice to see some friendly faces also out in the ether. And as Sean said, a lot of work that those guys have done on our machine, you know, has been really, really great. And it wouldn't be possible if Dr. Chen wasn't there helping. This is not a flash talk, and I'm sorry if you guys want to talk. If you guys want to talk afterwards, I'm happy to talk as long as you want. But I have all kinds of things to say. Or maybe Dr. Lou will get there before I'm done with this presentation, and you can go talk to him. Okay, I think I have to be over here because the clicker isn't working, but we'll see. Okay, so I want to share a little bit of the background with you. I think, as Sean said, one of the things that you'll see here is this is a real moment for proton therapy. And some of the things that we're stepping into with proton therapy actually are not so new, and were done in some of the older institutions and are being revisited for their optimum use today. The compact single room system, scan proton beams, and this launch back into the upright topology where it's much smaller and our system will fit into hospital systems. I'll cover all of that, and I'll point a bit at some of the things that we're going to do in the future. I will say, I just want to say thank you to Tina Yu over there. She's my boss. And I had a few bosses before her. I've been this whole journey with Mevion, and I think, you could say we've been a startup for a long time, and maybe we're not a startup anymore. So it's an exciting time for us. All right, just a little background. And I'm sure all you guys know this, and this is usually couched in a slightly different way, but 2 million people every year diagnosed with cancer. You know, we all know somebody, Sean. We all have friends and relatives. Half of them are going to get radiation therapy. Of that half, 1 million, 1.5% get proton therapy. And there's, often we have this discussion about, oh, why isn't it more than 1.5%? And I would offer to you that that's the wrong question. If you're one of those 980,000 people or 85,000 people, the question is, why not me? How come I don't get to get proton therapy? We have a lot of evidence that shows that it's better. It's principally been cost that's the barrier. And that's been our mission, to kind of drive this down. And you'll see as I go through this presentation that we've made some good progress here. Okay. Raise your hand if you know what proton therapy is. Oh, pretty good. Pretty good. Was that everybody? Not quite everybody. But what you see here, and this has been known for a long time, there's a patient on the table. On the left, you're treating them with an X-ray. You probably know the dose from an X-ray is exponential. It shoots right through, and that results in a lot of damage to healthy tissue. Protons aren't like that. This has been known for a long time. Protons are particles. They're not the waves like the photons. They don't decay exponentially. They go a certain distance and they stop. So in the case on the right, you see all that stuff, say, behind the heart, in this instance, not treated. Of course you want this. Of course you want this. But it's just historically been too complicated to make. And that's been our core mission the whole time, is to make this possible for everywhere. In the beginning, the proton therapy was laboratory based. It was only coming out of these big machines. And as it got started, they decided they would move into the hospitals. There was going to be one site in Boston and one site in California, and that would cover the whole US. That turns out not to be enough. Getting back to what's going on here, you see with this, this exponential here, that's the X-ray dose. And this black darker curve is the dose as a function of depth in the patient for the proton. See that nice hard edge on the dark curve where the protons are stopping. The X-ray dose keeps going on behind it. And so if you're being treated with an X-ray dose, which is how most treatments happen these days, you're going to get something like, double or maybe even 3 times as much dose as you need to treat the same thing. So we know, and this has been known for a long time, we know that this is dosimetrically better. And in a certain few particular cases, and the number of cases are growing, we also know that you can treat things that you couldn't actually treat with photons. So these are some slices of CT scans superposed with color washed dose maps. The redder it is, the more dose it is. And what you see is for a set of cases, on the top row, those are the dose profiles for X-rays, and on the bottom is the dose profiles for protons. And what's very clear is that there's so much extra dose from the X-ray beam. So this is just not in dispute. Everybody, I think, if it was you and you were in this path, you'd want the one on the bottom. And as I said, this technology has been around for quite some time. It actually, the guy circled there in red, Dick Wilson, wrote a paper in 1946. He was actually involved in the Manhattan Project, and was also a Quaker. So I don't know if you know anything about Quakers, but he had a lot of conflict about that, and because Quakers don't believe in participating in anything violent. And I think he felt like he had to give something back after the war. And so he was really, this paper down there on the right is foundational. You see the spike, the graph at the bottom right, where this Bragg peak is going up. And he's like, he was kind of the father of the launch of this therapy. That was in 1946. 1954, here in California, we treated a patient. This is not new, 70 years ago. It's just been too big and too cumbersome. And then in 1960, at the Harvard cyclotron, where I actually worked, I'm older than I look, they started treating brain AVMs and neuro disorders. So the class of things that can be treated with protons is really quite broad. And today we're at about 400,000 total. And we're really at a point where we're going to be able to provide this care for a lot more people. So what you see on the left there, I'm not that old, but that was the machine at the Harvard cyclotron. And it weighed 641 tons. And of course, the beam could only come out sideways, could only come out like this. And then it went down, followed the black arrow through a bunch of rooms, through some hallways, around the corner, and eventually got into this treatment room, where you see the green tank. There was some beam shaping assembly in the green tank. And a person was seated on a chair. In this case, they're doing a retinoblastoma, which protons are very good for. And there was no other way to do it because that thing on the left was so heavy. So, and importantly, the same facility, this was about 1980. I wasn't there quite yet. They know because the proton dose is so much less, it's especially good for kids. And that's been one of the key indications right along is, the kid's going to live a long time. Some of these kids are even cured. And you don't want the secondary effects from all that extra dose. And here's a kid, and I want you to notice this kid. You can kind of see in the background, the proton beam is coming out of this thing with this aperture here. This kid is what we would call seated or upright, 1980, right? So, and he's anesthetized, and these were very good. These were very good treatments at the time. So that's kind of the history. This has been going on a long time, and the care stayed in these lab settings, which the doctors didn't like that much. They didn't like working in the lab settings. And then I think it was 2004, whoever it is, the medical people, CMS, they decided, okay, proton therapy is a real thing, and we're going to support the commercial development of that. And before that, commercial companies weren't really venturing into that space. That was the moment at which we launched. And for me, as an accelerator physicist, that was really a dream job. And what did we do? It's been, in putting this together, it's been 20 years now, so it's been a while. We developed the world's most compact superconducting synchrocyclotron. It's like this big. And that's like 4 or 5 times smaller than anybody has ever done before. We developed a super efficient beamline delivery architecture. I'll show you that. We developed the only system that's got the proton delivery source on the gantry, much like the TrueBeam kind of architectures. And we're also the ones who developed the world's first single room proton system. So this is back in 2006, the very beginning. And there was a lot of technical question about were we going to be able to make this work. Tina jokes about the napkin sketch, and there was a napkin sketch for how we're going to make this thing work. One of the key elements is the very high magnetic field synchrocyclotron. And people weren't sure that we were going to be able to get the ion source out of the ions, the proton ions out of the very center. And the whole thing couldn't stand together. So in the very beginning, to demonstrate this, we bought this NMR magnet. You may recognize that. That's like an 8 Tesla NMR magnet. And inside it, we put this micro cyclotron. That was an isochronous cyclotron, tiny, tiny little one. And what you see on the right is we had this endoscopic camera that went in there. And if I just click this button here, you watch this. Okay, so that little fluorescent light, that's the proton plasma. Protons are purple. And it doesn't look like much, but you see the green dots as they're swirling out there, and you can actually see the separation in it. Those are successive turns in a cyclotron of the proton beam out to 1 MeV in this size, right? So already we hired kind of a pretty crackerjack team of engineers, physicists, software engineers. There were only 20 of us at the beginning, and we were each knocking off corners of this to establish the feasibility of this system. The big enabling piece was the superconducting magnet. So what you see here is the coil for the superconducting magnet. And that's built on a special superconductor called niobium-3 tin that's capable of carrying enormous currents and current densities at very cold temperatures. So if you make that material 4 degrees Kelvin, minus whatever 290 or that will carry 2,000 amps in a wire that's like 3 millimeters by 4 millimeters. Think about that, right? The comparable size for a wire made of copper is like this. And that goes inside. What you see on the right there is the cyclotron itself. That thing is only 15 tons, and it's about the size of this desk here. It's still a heavy, big thing, but compared to what it was replacing, it's remember the thing I showed you earlier, the Harvard cyclotron, about the same energy, 641 tons. So it's running at 2000 amps. It's got a field in there of 8.5 Tesla, maybe even a little more near the coil. Typical MRI, if you go in there, might be 1.5 Tesla. So this is a very strong field in there. And there are challenges and, actually a lot of good engineering to put that kind of system together. It also is incredibly efficient. The cyclotron, as I hope you know, is a circular machine. So a proton is accelerated over and over and over again, 75,000 times in the case of our machine. So if you unrolled that, that's the same as a proton machine that's, longer than a marathon, 30 miles or something like that. So it's incredibly, there just isn't another practical way to make protons of this energy except circular periodic machines. And then at the very bottom here, this thing makes on the order of 1 to 100 nanoamps. And for the folks who want to do flash, they like this higher current. They'd probably like even more, to access dose rates where there's some other very interesting physics going on. And it's been an area that I know Dr. Lamoni and Dr. Maxim have an interest in and have pursued sometimes. So it's possible to do that kind of work with this machine as well. So then what do? We took this thing and we put it on that gantry there. That's one of our centers down in Florida on the right. And you can see that 15-ton thing is rotating around the patient. Why did we do that? Why did we build that dumb thing? Any guesses? Okay, yeah. Why did we build it? Well, we could do beams from different directions. Yeah. Anyway, yes, you're right. We want to avoid organs at risk. Exactly. We built it, in my mind, because the doctors said they wanted to treat their patients supine. Right? And, who are the physicists? I said, we're used to having our patients supine. We want them lying on their backs. We want to do just what you said, Charles. We want to miss all the organs at risk. That means you have to move this big thing around. This thing that we built was the smallest. We finished this one in about 2013. It was the smallest one of this size by already a factor of between 5 and 10. It's still kind of a big thing. That room is 24 feet, within a couple feet, yeah. And we looked at doing a single-ended gantry, which if this had been built with a single-ended gantry, it would look a lot more like what you see in the X-ray booths, like a true beam, right? But because of the load on this thing, we decided to carry it from both sides. And then, as I said, one of the big important indications for protons is pediatrics. And here's the first patient that we treated in St. Louis, and that felt really, really good to get that done. A lot of these little kids, get better, and they're happy to not have received all that extra radiations. And is that washed out on the? Anyway, the intent of what we're trying to do here, what you see there is an X-ray photon machine on the left and our proton machine on the right. And they look kind of the same. At the time, that was the smallest proton machine that had ever been built in that context. It's still kind of big. I showed you what was under the hood just a minute ago. And so we had a lot of good luck with that. And that's, was our generation 1 machine, but it still wasn't exactly what people wanted, I would say. And what happened was the guys in Europe, if we know any Europeans, they started this effort on scan proton beams, which was a good move. And what's a scan proton beam? Instead of putting foils and material in and shaping the beams. This is from PSI, from the Paul Scherrer Institute. And they made more like an old-fashioned television screen where a raster scan will move the proton beam all over the patient. That turns out to be more efficient. That turns out to be easier on the workflow. You don't need to build these complicated apertures that take a long time and have to be quality. And it's just more flexible because each one of those dots can be intensity modulated. So that's called intensity modulated proton therapy. And the degrees of freedom in being able to modulate each one of those spots gives you a pretty fine knife to tailor the radiation exactly the way you want. And starting in about, I want to say 2015 or so, that really became the dominant vector for proton therapy. Everybody wanted to go that way. That's all that anybody makes anymore. They don't make the scattering systems anymore. So we did the same thing. We weren't the first. And as I mentioned, when we're thinking about this, making this thing small, accessible, affordable, we paid special attention to not making it too large. One of the things that happens in the US laboratories is they're not necessarily, and I came from one of those places, they're not necessarily the most cost conscious about the architecture of how you build something. And that was the opposite of our approach. We were getting leaned on only put in the things that you need to do to provide the therapy. Don't put in extra stuff. It's like designing a rocket. If you got to make it, go to the moon, you don't want to put in junk you don't need that can fail. And in our scanning system, which has many of the components of everybody else's scanning system, there are four main things. But principally, it's only 2 meters long. It's only from the exit of the cyclotron, which in this figure is right here, to the isocenter, to the target. It's about 2 meters. And in that space, we have a scanning magnet. It deflects the beam in both planes. We have some dosimetry that measures the character of the beam. Importantly, in its transverse dimension, remember I told you protons stop. So all we have there is information about how much and where it is laterally. That's pretty standard. And then we built two things. Again, we weren't the first, but because it's the scanning proton beam is working like this 3D printer, you want to be able to adjust the depth. And the way we do that is with this thing called a range shifter. And by putting slight thicknesses of material, we can set any depth. And then at the very last, we have a proton-specific multi-leaf collimator, which is the only one that's been successfully deployed. And we take advantage of the scan beam architecture to make a pretty elegant device there. I'll show you that in just a second. So we were pretty happy with this. And it was nice to not be first here because we got to see what everybody else had done and maybe take some of their better choices and improve on them. So here's a beam being scanned into a water tank. This was at our factory, I don't know, 15 years ago. And it's a dry cleaning fluid. That's not. And there you see it going left to right. And that's real time for, you can see the higher dose in the end of the Bragg peak. And you can imagine taking that thing, it's a little saturated in this image, and scanning it all over the tumor and missing everything else. The edges on the top and the bottom are cleaned up by our collimator that's not in use for this video. And then we did this other special thing. This device on the right is the range shifter, which we use to do the 3D printing of the depth. And what you see there is this laser is emulating the delivery of the proton beam. And that follows the plates as they're moving, which results in a very, very short transition time from one layer to the next, between 50 and 100 milliseconds, which is as fast as anybody can go. One of the things that people have been after is they'd like to do really fast deliveries. I remember when Dr. Liu approached us a while ago, he was looking at stop motion in a different architecture to deliver a whole radiation field in less than a second to manage motion stuff. So the delivery of these doses quickly is important. And then this piece, which is at the end of the line in this scanning system, is our proton multi-leaf collimator. You can see it right here. And the collimator? Yeah, material. Nickel. And nickel has comparable density to iron, but it's got a low neutron production cross section. It was a good choice for a number of reasons. You want a relatively high density, but probably not brass or tungsten right there. And if we look at this,
I'm surprised we needed that tiny pulse.
well, it turns out
Changing the pulse width to, you can change the dose.
we have all the degrees of freedom in this printer, if you will. We can change the pulse width to adjust the intensity of each spot. We can change the lateral position of each spot. We can change the range of each spot with the range shifter. It turns out that even for any spot scanning system, you get the brightest edge, you get the brightest lateral penumbra, the best fall off by going over the edge of the collimator. So using that in addition to the spot scanning gives the clinicians all the degrees of freedom to tailor the treatment any way they want. Yeah.
So you still use them.
Yeah, you use multi-leaf, you use the IMPT, you use the range shifter, and you use the magnet to set it wherever you want. And, oh yeah, there you go. And people had tried to build these things before. They tried at the University of Pennsylvania. I'd say those systems were not very successful because they were built with large leaves. This one we did nested motion. So the blocking area here only needs to be as big as one spot. And that allows us, again, to make a very compact, efficient delivery system. So what does that do? Again, here's a dose map of this is a slice right through the middle of your head right here. And you're treating, I think this is a paranasal sinus. Probably someone knows better than me. This is standard IMPT. And you can see these gradients, and you want the dose in here in the red part, and then you want nothing outside. This is without that aperture, which is how most other people do it. If you just have a single cut piece of brass, all you can do is a single projection. You see these straight lines here, and that also is not quite as conformal as you'd like. But with this little computer-controlled aperture, we can actually trim every layer to the desired property. And what you see there is we can carve out the dose all along the way. So it's really the maximum degrees of freedom to do the best possible with the dose. Okay, so we built a small cyclotron. We built a really great scanning beamline. I'd say it was still a little too big. I showed you that movie of the proton system going around the patient. And the hospitals would like these care devices, but you can imagine it's kind of a big job to find the space to put something like that in and get all the power. And so even our small scanning system, which we were pretty happy with, is still not quite small enough to meet the needs of most hospitals. So what did we do? There were a bunch of people who helped make this happen, but Rock Mackey at Leo Cancer Care, who's the father of tomotherapy, which is a ring geometry, enclosed helical ring geometry, and really moved the field of radiotherapy on the proton side. Said, okay, let's try upright. So we were working with his company and Dr. Liu up in Stanford, who was critical for putting this development effort together. I'm not sure it would have come together without the Stanford team. And we launched on the following product. And there's the accelerator in the back. There's a chair. That's a diagnostic CT scanner. And what you notice now is it's not nearly so big. Not only is it not nearly so big, it fits in all these existing LINAC vaults. And that's a big deal. Interestingly, Charles, to your point earlier, you're saying, why do we have the gantry? Because we want to miss all the critical organs. Yes. This is intrinsically a coplanar geometry. In the gantry-based system, the beam goes around like this. The robotic couch can also, that's more of a 4-pi system. In this system, it's coplanar. The beams are all coplanar. The beam comes like this, you rotate the patient, right? So the degrees of freedom are not the same. The question is, can you still do a pretty good job with that? And that is the same path that Rock Mackey took with tomotherapy that turned into, well, not only Accuray, but later on the Halcyon project from Varian that's been enormously successful. So I think the world thinks that the answer is for sure yes. We have all these degrees of freedom in the delivery system now that we get to combine with these coplanar fields to treat whatever indications we want. So now you see, so this is and this I think went faster maybe even than we expected. A lot of people were willing to step into this space even before we had all of our clearances. After we got our clearance, even more. But so this is an example on the left of a place in New Jersey. You see the LINAC on the left, and there's a room, and it fits right in that thing. And then the one on the right is another instance in Nebraska, which is not so different from some of the spaces that are around here. Again, a key piece of this technology is this upright chair. It's called upright therapy because the patient isn't lying down, they're upright. And if you remember the picture I showed you of the sort of Frankenstein-looking laboratory with the person in the mask, we're a lot better at building things and mechanized things and robots than we were in 1980. So what goes along with this infrastructure is all of the work that's been learned in the world about how to handle immobilization and robotics since 1980. Importantly, they learned in the restraint side some very important things about this shin rest, so the patient doesn't move during the course of the therapy. And if you look at the top here, this is a diagnostic CT. So I don't know if you know the difference between diagnostic CT and say cone beam CT, but in general, when you go for a course of radiotherapy, one of the things they'll do right up front is take a diagnostic CT of you, and some doctor, very smart person will say, okay, this is the place. Often they don't do that again, for a couple of weeks, and maybe things are changing. So they're blind if they don't have continuous access to this high resolution image. This is what's driving image guided therapy. And in our systems, all of our systems, the slightly larger one too, we now provide this diagnostic CT with them, which enables people to change the prescription as they see things changing. Of course, you want that. And what I showed you before was a rendering. This is what's right up there, just up the coast a little bit. And I was just there myself for the first time just a few days ago, and I think it looks pretty good. And we'll see how the Stanford team goes with launching this thing, but it's going to treat its first patient probably in the next couple of months. And my expectation is that this is going to be pretty successful. And because of its packaging and its ease of use, everyone's going to want it, I hope. But one of the things, yeah.
I see the aim of the diagnostic CT is also to register
Yes.
the main CT and then guide the beam, right?
Yeah. So every day there's a planning CT that might have been taken with this CT. The CT has the quality to do that. The patient, because they might be treated 20 times, yes is the short answer. This is also used to measure the anatomy and make sure the anatomy is in the right place every day. Yeah.
And if during the therapy, the patient move or something, do you real time correct for those?
Well, that is a really great question, because that's kind of at the heart of image-guided radiotherapy. And you'll see that, some of your colleagues here are working on exactly that problem. The CT, and by the way, on the photon side, they're a little ahead of where we are on the proton side with that problem. You would like, ideally, to monitor continuously the anatomy while you're delivering the radiation. Everybody wants to do that. And it's a little tricky because it's inside your body and we're built like Jello and stuff is moving around. The CT is a really tricky device to use. So we do not measure this while the beam is delivered. I don't think anyone does, as far as I'm aware. You can take projections, X-rays, but as you'll see from Sean and Dr. Chen out there are a number of other approaches to do exactly what you're saying, which is to monitor the anatomy while you're delivering the therapy. And of course, the field is going there. Those things will be rolled out, over the next years or so, not that many years, maybe. And the degrees of freedom that they have on the photon side are going to get added to the proton side, for sure. In particular, I mentioned about the coplanar and the Rock-Mackie and tomotherapy. You can see this is an image of, from above the patient's head, a bunch of beams sequentially delivered as you go around. And we were challenged a bit by, show us that that's just as good as the other system. So we've been quite successful with that in some measure because there are so many projections. So there's this kind of cool math problem that goes on. Each projection has, if you think about all the choices, each projection has all the energies, has all the orientations, has, all the positions of the MLC. So it's this giant optimization problem to make the best dose given all these degrees of freedom, which we didn't have the horsepower for computationally, 25 years ago. And now it's possible to solve these problems in a way that makes the therapy, I'd say, even better than the IMPT of the systems just 10 years ago. This transition also happened in the photon space, I would say. It happened, people here probably know better than me, happened in the photon space, I don't know, when they went from IMRT to VMAT, all of a sudden, every single treatment is covering all the, 360 degrees of angle. And of course, the computer can find a better solution when you give it more degrees of freedom to solve the problem. And here's an example of that. Again, a slice, now we're a little lower here, right here, going through and the panel on the right is what you get if you just hit this, have a few portals, not all the way around. And you can see how this is lumpier and not as smooth. And with this direct arc, this arc therapy, which we come from here's your spinal cord, and you don't want any dose on that. And it's moving away from that. That's critical. And you also want really good coverage of what's inside these blue circles. And it's this better. I think it's also going to be easier. Importantly, delivering radiotherapy is a little bit of it's a high expertise kind of job. And when you have a way into the problem that's self-similar, like this arc is, I always do the same thing. I start with this thing and it goes all the way around and open the door for the computer to find the problem. It's going to make it much easier to provide this therapy and maybe need not quite so expert people on the planning side, which has been a big barrier for, some of these, even today in these sites, we still have a hard time finding qualified people to do all this work. Okay, then I just have a bit more. I want to point on a couple future directions. Sorry, Charles, this is all I have on this. We can talk later. But we had a number of people, Dr. Liu, Peter Maxim, Charles, who want to chase this interesting phenomenon with correct me if I say something wrong, the flash effect, where if you deliver dose at a very high rate, you can see this differential effect between the healthy tissue and the tumor tissue that is favorable for sparing normal tissues. But it's complicated, and go ask him if you want to know what's going on. So we, on our platform, on our clinical platform, made a way for people to do research and translate this, which is still a bit of work, into therapy. We'll see how this goes, but it was, many of our patients, many of our customers, I would say, are interested to pursue this research. Another thing is that, and this is again in this arc delivery, protons, unlike photons go in and have a kind of constant, what's called relative biological effectiveness. Their ability to damage tissue doesn't depend too much on what energy they are or what depth they are. The protons, actually, if they're going slower, they have this thing called LET, linear energy transfer. So it's kind of a really remarkable thing to think about. So protons are like a bunch of needles. You can think of them as a bunch of needles going through you, and they go zap, zap, zap to the DNA as they go through. And depending how, like the cluster of the zapping and the density of the zapping, the linear energy transfer, you can do more or less damage to the DNA, the particular DNA, as you go through. A little damage can be repaired. And this property, the relative biological effectiveness, which is measured empirically often in cell survivals, is complicated for the slowing protons. What we know is it's higher as the protons slow down. So they actually do more damage at the end of range. Now we have this complicated planning software, these complicated delivery engines. We're still using a constant scaling factor for this effect. We know it's wrong. But with this kind of delivery and with this kind of degrees of freedom, on both the planning side in the computer system and our delivery side, we are now going to be able to optimize this quality of LET deliveries for patients. That's a space that hasn't been explored for protons. So protons have kind of had this barrier of adoption, and there are these windows where we can make it better and better and better. And in order to make it better and better, people need access to the equipment. Another one is you had just asked about, is the CT watching it during the system? So during the delivery? No. But one of the things people would like to do, and this I would say is a work in progress, is they would like to look at the patient with the information that they did to align them and use that to, if they want to adjust the prescription, do that very same day. So if they see something they don't quite like, not just try, because we're not rigid bodies. Maybe the thing got smaller or changed, or maybe your sinuses were full, or, we're kind of like bags of Jello. So of course, people want to measure, like if you're a surgeon, you're going in there, you're reacting to what you see at the moment. In radiotherapy, you have to react, your plan was made 2 weeks ago. So with these diagnostic CTs, which are available in all our systems, on the day of now, we have really good information to change the plan if we want to. And so one of our customers, I don't need you to follow the details of those boxes on the right. And Sean, for example, is thinking of something similar in his workflow. We would acquire this information, and then in that same treatment session, we can now go fast enough to adjust it that same day. That was done by the folks in St. Louis, and that's kind of a big step forward. It's what's called adaptive radiotherapy, same day adaptive, on the table adaptive. What you were talking about, which is still another step, I would call real-time adaptive. And of course, people would like to go there too. In order to do real-time adaptive, we need to know not just where the beam is going in its transverse directions, we need to know where it's stopping, which is kind of one of the historical bugaboos of proton therapy. And oh, look at this. So this is work from Sean and his team and Dr. Chen in Oklahoma. And they have a phantom patient there on the table.
No, that's a real person.
Okay. Excuse me. They have a real person. In the middle is an ultrasound detector. And it turns out that you can hear the proton beam with the ultrasound detector. So if you look at the images on the right, those are from CT scans. That crisp anatomical image is the CT scan. But what has been the largest source of uncertainty in the delivery of proton therapy is where is exactly, you see that little dose map, where is that going? Where is that dose map going when we zap in? We know the direction it went in when we launched it, but we don't know where it stops. And because of that, one of the things that everybody has done is they've padded the back edge. Like, I'm not really sure how far it's going. I don't want to miss that thing. So just put a bunch of extra on. So of course we want to do this. And it's actually talk to Sean if you want to know more about this, or talk to Dr. Chen. But you'll see that the radioacoustic imaging is giving us information that is similar, but not identical to what the plan said. So we're going to go full circle on this, and that's going to tighten things up, and that's going to be better for everyone. People would like to have something like this, something that measured the range. Of course you want to see where it stops all the time, and it's just been a challenge. But this kind of technology is opening the door for that kind of improvement, I would say. And that's all I had. This is our team in Stanford. The woman in the red is our service. She's in charge of our service team. And I don't know if any of you will have a chance to get up there, but we're really excited to turn that thing on. And thank you very much. Happy to field any questions, or if you have any questions for any of my colleagues. Yeah.
Thank you for the talk. Really well. I had a question on the difference between the version that we're seeing in this picture versus the rotating gantry version.
Okay.
So you explained like that there was a 2 meter distance between the cyclotron, you have a bunch of like sensing, hardware. And so-
Yep.
In order to decrease the size, do you have to sacrifice any of those type of like quality control things, dosimeters, or?
I would say no. It's still actually the same distance. It's actually a tiny bit longer in this system. The reason the gantry system becomes so, it's not really much bigger in its footprint. But if you take that 2 meters that was filled with those things, it's a good question. You have to rotate it into a circle or a half circle. So that projects a 3-story shape. Is that what you were? No.
No, I mean, you had a good question.
Okay. Yeah.
I have two questions. The first question related to the question I asked before. You know, if you're able to modulate the beam on time,
Right.
then fundamentally you should be able to do without multi-leaf follow. There's something I'm missing.
Oh, there are people who do not use a multi-leaf collimator. So it's okay. It's okay. And I would say that depends on how sharp you want the edge. Because it's like the size of the paintbrush. When we modulate the beam on time, we're modulating when it appears in time, not where it goes in space.
Right, but you know where you are.
Yes.
Because you are scanning.
Oh, so a way to, maybe another way to think about it is if, and you can do similar triangles to get an effective penumbra. You can never do better than a razor blade edge. And that's what a collimator is doing. If you want a steep gradient, the mechanical edge will do better than this, even the smallest paintbrushes that we can make, because the paintbrushes are Gaussian.
The size.
Yes, yeah.
I see.
Yeah, sorry, I wasn't clear about that. All of these paintbrush sizes have these Gaussian distributions. And if you want it tighter, you can put an edge on it. So we'll see in our plan, sometimes they'll use it, especially if it's really close to something they care about. Or if it's not, then they let a little more dose, into the normal tissue.
So my second question, if you have a long term, let's say the patient is breathing, so you have your tumor volume moving.
Yeah,
I'm just thinking that if you have a CT scan up there, you scan right before treatment, and there's automated segmentation, so you define the tumor volume in 3D space, and you have fast treatment, and you could scan, know exactly where the tumor is, shoot, do again, but you have to have that segmentation. You have to know where the actual tumor volume is, and I think that might be the most difficult.
it's a great question, and it is very challenging. It's a great question. So in the case of a lung tumor and there are people here who can, Dr. Chen or, some of these guys, Dr. Max, who could answer that better. In the case of a lung tumor that's moving around, sometimes they'll just make a bigger target that covers the extent of the motion. Not so great, but safe. Sometimes they'll take a 4D CT scan, so they measure the position of the tumor at all the phases of the breathing motion and put on something like a belt. I saw Dr. Chen doing this, and gate only when the right phase of the breathing motion. Sometimes they may put an ultrasound detector on there so you can see these interfaces and know where you are. Managing the motion targets for radiotherapy delivery, I'd say, is a challenge. And we know there are opportunities to do better. And we see advancement on the photon side, and we see advancement on the proton side. Yeah.
I mean, I would say that the fundamental issue in radiotherapy is when we talk about precision medicine, for us, really focus on radiation being on tumor and square as much as around the normal tissue. the remaining barrier for a most precise radiotherapy is organ motion. Everything in the body moves very free for the blood spilling out. And so we implemented many of these techniques that Dr. Roth just explained. We synchronize the beat of the respiratory cycle. We ask patients to hold their breath, freeze motion. And I think where flash radiotherapy that comes in addition to the benefits of the radiologic side, I think flash radiotherapy is the future of radiotherapy in terms of you deliver the radiation faster than the time scale of physiologic motion that you overcome that hurdle. Current radio technologies, every vendor claims a motion management strategy, and everything predicates on the fact that the delivery of the radiation is much longer at the time scale of physiologic motion, like what happens, or your respiratory cycle. And so overcoming that barrier is really one of the fundamental issues that we're looking for. Make treatment faster.
I'm just thinking the fact.
Exactly.
So if you could image right now, and let's say real on that, and I think with machine learning and possible computational, that will be possible eventually. But then if you're able to deliver image treat in a fraction of a second, you overcome all
That's what.
Right. And I couldn't agree more. And I think, you know, when the field gets there, it's all gonna be done that way, you know. Yeah, Leo. Oh,
You can.
do I have to enable?
No, they can just unmute themselves, they can ask questions. Maybe you can use the microphone.
Can you just unmute yourself?
May I ask a question?
Yes, of course,
Oh,
of course.
thank you. My name is Dr. Tadir. I apologize for being a clinician, or even worse, to be a surgeon. Now, when a clinician or a surgeon speaks about tumor therapy, he or she means removal of the tissue. What kind of biological effects are expected? Is it a kind of thermal effect? Is it ablation, coagulation, any kind of tissue removal? What is the bottom line of this therapy or treatment or whatever you call it? And my other question, since you refer to image-guided or CT-guided and you speak about soft tissue, what about MR-guided in this context?
I think I'd like to defer to one of my friends on this. Peter, yeah.
The tissue damage what we're doing right now is I mean, in comparison, what you're doing, excising something, removing tissue, what radiation therapy does is ultimately DNA damage. So we are damaging the DNA of the tumor, so it cannot replicate anymore, and it won't grow, and eventually dies. So it's a similar effect. But we do type of surgeries, what we call radiosurgeries, where we use, instead of a scalpel, we use a fine radiation beam to treat lung cancers, brain cancers, instead of going in there. The advantage with that is that you don't have to use anesthesia. It's painless. A patient with other comorbidities probably cannot tolerate anesthesia, so radiosurgery is the way to do it. And if you look at early stage lung cancer, the historical data to handling lung cancer was, really doing a surgery on these tumors. But recent data have shown that radiosurgery rivals outcomes with the surgery without the comorbidities, without the anesthesia, without the effects that you are doing. But ultimately, everything boils down to DNA damage.
Okay, because the advantages of being non-invasive therapy is obvious. When I compare that, for example, to MR-guided focused ultrasound, this is heat focused on the target tissue. Unlike that, I understand that you're talking about simply DNA damage and not tissue removal.
Correct.
Am I right?
Yeah.
Am I correct?
Well, the advantage to HIFU, what you're referring to, for example, is that we do accurately now know the dose deposition. We can dial in very precisely what dose we need to do, ablative doses to kill the tumors. We don't need an MRI guidance or the MRI to figure out what the heat deposition happened with the cryoablation. So the dosimetry is much, much more accurate. And that's one of the strengths of radiotherapy that we have now. Over the 60 years, we have developed these mathematical models to really accurately calculate the dose deposition in the body. So we know exactly what we're doing. And that is all being backed with clinical studies.
Okay, thanks. Thank you.
Any other questions or?
Am I anything?
Well, there is technology out there. So there are companies that build these X-ray systems with MR guidance. So you could see now in real time tumor tissue motion or, motion in general on a planar image, usually on a sagittal image through the tumor plane. So the technology is out there and their centers, just even our competitors are using that. That doing MR with the proton system is much, much more challenging, if not impossible. But for X-ray technologies, yes, there are companies and technologies out there.
Thank you.
Okay, thank you all very much. Really appreciate it. It was great to be in Southern California.